Hello friends, welcome to Stuff Networks. In today's video, I will explain everything about OSPF, Open Shortest Path first. We will understand how it works, how to configure it, and why it is one of the most important routing protocol. So watch till end. I'm sure this video will help you a lot. OSPF or Open Shortest Path First is an interior gateway protocol used to dynamically manage network routes within a single autonomous system. It's a link state routing protocol that uses the Dijkstra algorithm to calculate the most efficient paths, builds a map of the network topology, and is widely used in large enterprise and service providers networks. Unlike protocol that send periodic updates, OSPF sends updates only when a network change occurs. Make it efficient and scalable. How it works? Neighbor discovery. Routers use hello packets to discover and establish a relationship with neighboring routers. Link state advertisements LSAs. Once adjacencies are formed, routers exchange LSAs, which are packets containing information about their connect links and cost. Topology map. Each router builds a complete map of network topology using the LSAs from all other routers in its area. Shortest path calculation. Each router independently runs the Dijkstra algorithm, also called the shortest path first or SPF algorithm, on its topology map to calculate the shortest path to every destination. Routing table. The results are used to populate each router's IP routing table with the best routes with each other. OSPF metric and cost calculation. OSPF metric is cost calculated by dividing a reference bandwidth by the interface bandwidth. The default reference bandwidth is 100 Mbps, so a 10 Mbps Ethernet interface has a cost of 10. The shortest path first SPF algorithm then builds a shortest path tree for each area, summing the cost of links in each potential path to find the route with the lowest total cumulative cost to a destination. Now, OSPF cost calculation metric. OSPF uses cost as its metric, which is inversely proportional to bandwidth. Higher bandwidth interfaces have a lower cost. Formula. You can see the formula of cost here: reference bandwidth and interface bandwidth. Now, reference bandwidth. The default reference bandwidth is 100 Mbps, but it can be changed to a higher value to better differentiate between modern high-speed links like gigabit Ethernet. Now, next page. You can see the cost example here. You can take a screenshot of it or write it in your notebook. Shortest path first, SPF tree and path selection. How it works. Each router maintains its own instance of the OSPF protocol and independently runs the SPF algorithm to build a shortest path tree for each area it belongs to. Tree structure. This tree is routed at the router itself with the destination network as it leaves. Cumulative cost. The SPF algorithm calculates the cumulative cost for every possible path to a destination by summing the cost of all the outgoing interfaces in that path. Best path selection. The router selects the path with the lowest total cumulative cost as the best path and adds it to its routing table. Example, if a router has two paths to a destination, it will compare the total cost of path A against the total cost of path B and choose the one of the lower cumulative cost. OSPF timers. OSPF timers include the hello interval, frequency of hello packets, dead interval, time to wait before declaring a neighbor down, retransmit interval, time between retransmitting, link state advertisement, LSAs, and transmit delay, time for a router to send an LSA. The hello and dead interval must match for neighbor agency, with the dead interval typically set to 4 times the hello interval. Default timers vary by network type. For example, a 10-second hello interval and 40 seconds dead interval for Ethernet versus 30 seconds and 120 seconds of non-broadcast networks. First is hello interval. What it is? The length of time in seconds that a router waits before sending an OSPF hello packet out of an interface. Purpose: to maintain a relationship with neighbors and ensure they are still active. Default values: 10 seconds for broadcast and point-to-point networks, example Ethernet. 30 seconds for non-broadcast multi-access networks, example frame relay and ATM. Configuration: must match on both sides of a link for adjacency to form. Now, second is dead interval. What it is? The period of time in seconds that a router will wait without receiving a hello packet from a neighbor before declaring that neighbor down. Purpose: to determine when a neighbor is no longer reachable and should be removed from the routing table. Default value 4 times the value of the hello interval. 40 seconds on broadcast and point-to-point networks 4 by 10 seconds. 120 seconds on non-broadcast networks 4 by 30 seconds. Now, the third is retransmit interval. What it is? The time in seconds between retransmitting and link state advertisement LSA to a neighbor. Purpose: to resend LSAs that were not acknowledged, ensuring all routers have the most up-to-date routing information. Default value 5 seconds regardless of our network type. Configuration: the limit of retransmission can be changed or disabled. Now, fourth is transmit delay. What it is? The time in seconds it takes for a router to send an LSA. Purpose: to account for the delay in transmitting an LSA over the network. Default value 1 second regardless of network type. OSPF network types. OSPF supports several network types: point-to-point for single links, broadcast multi-access for Ethernet LANs, non-broadcast multi-access NBMA for legacy networks like frame relay that lack broadcast capabilities, and point-to-multipoint for hub and spoke WAN topologies. Each type dictates how routers discover neighbors and handle adjacencies and the DR/BDR election process. Let's talk about our first network, point-to-point, used for direct router to router links with no other routers on the link. No DR/BDR election is performed. Example: a serial link or a VPN connection between two sites. Now, second is broadcast multi-access, default for Ethernet LANs which support broadcasting to all connected devices. A DR and BDR are elected to manage the network, reducing the number of adjacencies needed. All OSPF routers send hellos to 224.0.0.5 and DR/BDR routers send hellos to 224.0.0.6. Now, third is non-broadcast multi-access (NBMA), used for networks that are multi-access but do not support broadcasting, such as legacy frame, relay, or ATM network. A DR/BDR election occurs. Router must be manually configured to become neighbors because they cannot rely on broadcast to discover them. Now, point-to-multipoint, used in hub and spoke or partially meshed topologies, often over a non-broadcast network like frame relay. No DR/BDR election is performed. It models the network as a series of point-to-point connections, with each router forming an adjacency with each neighbor it can reach. A point-to-multipoint non-broadcast PTMP and NB variation exists for more granular control, which uses unicast and requires manual neighbor configuration. Now, last is OSPF multicast addressing, 224.0.0.5. All OSPF routers send hellos and other OSPF packets to this address. The address is used to communicate with all other OSPF routers on the local segment regardless of their role. 224.0.0.6. This address is used by DR and BDR routers to send hellos and other OSPF packets to all other OSPF routers on the segment. It allows DR/BDR routers to efficiently exchange routing information with all other neighbors without sending individual packets to each other. Now, let's talk about message in OSPF. In OSPF, routers exchange 5 distinct message types to build and maintain an accurate loop-free map of the network topology. This map, known as the Link State Database (LSDB), is synchronized among all routers in an area, allowing them to calculate the best path to any destination using the Dijkstra shortest path first SPF algorithm. Types of messages in OSPF. All OSPF packets share a standard 24-bit header and are encapsulated directly into IP packets using protocol number 89. Type 1 is hello packet. These are sent periodically every 10 seconds of default or broadcast network. to discover and maintain neighbor relationship and elect a designated router DR and backup designated router BDR. Important fields are network mask, router must have a matching subnet mask to become neighbors. Hello dead intervals, the interval timers must match between neighbors to establish agency. Router priority used in the DR-BDR election process, a priority of 0 makes a router eligible. Router IDs, a list of router IDs of known neighbors to ensure bidirectional communication. DR-BDR IP address identifies the IP address of the elected DR and BDR on the network segment. Now, type 2 is data description DBD packet. These packets contain a summary of a router's LSDB and are used to check the inconsistencies between neighboring routers during the database synchronization process. Important fields are master slave flag. The router with the highest router ID become the master and control the DBD exchange process. Sequence number. The master of slave use this to ensure DBD packets and transmit correctly. LSA headers. Each DBD contain headers for the LSAs in the router's LSDB, not the full LSA information. Now, type 3 is link state request LSR packet. After exchanging DBD packets, a router sends a LSR to request the full content of any LSAs that are missing or outdated in its own LSDB. Important fields are link state type specifies the type of LSA being requested. Link state ID uniquely identifies the LSA. Advertising router, the router that originally advertised the LSA. Now type 4 link state update LSU packet. This packet is responsible to an LSR and contain the full LSA information requested. It is also used to flood new or changed LSAs through the network. Important fields are number of LSAs specify how many LSAs are included in the packet. LSAs contain the complete LSA data which describes a piece of the network topology. Link state acknowledgement LSAck packet type 5. This packet acknowledges the receipt of LSU's packet message ensuring reliable flooding to link state information. LSAcks are known one or more LSAcks. Now, here are some important points. Reliability mechanism. The LSAcks message provides reliability in the flood process as OSPF explicitly requires confirmation of each LSA. Multiple acknowledgements. A single LSAck can acknowledge the receipt of multiple LSAs. Unicast and multicast. LSAcks are sent via unicast to acknowledge specifies LSUs or multicast to acknowledge multiple LSAs at once. Thanks for watching. If you found this video helpful, don't forget to like, share and subscribe, and also press the bell icon for future updates.